Welcome back. So today we're going to look in more detail at shared memory synchronization. So we're basically going to focus on the bugs that can occur in shared memory programming. And so these are called concurrency bugs. So what we saw last time was that if you have multiple concurrent threads and they're accessing shared pieces of data, right, then if you don't do any synchronization on those accesses, then you could have bugs occurring. Right, so we saw this example where two threads try to increment a value, but depending on how the threads execute, the value only gets incremented once. Right, it should be incremented twice. So basically, these bugs occur because when you have multiple concurrent threads, the threads can be interleaved. Their execution can be interleaved in any order. Okay, because you really don't have any control over the speed of execution of the threads. Right, so that's up to the runtime environment and whatever happens during runtime. So sometimes you could get these interleavings that cause your code to crash. Okay, and the reason this is hard to deal with, the reason it's hard to eliminate concurrency bugs is that usually our method for eliminating bugs is just to do a lot of testing. Okay, but for these concurrency bugs, since they depend on the interleaving, they basically occur at random times. Right, because you can run the code multiple times, and each time a different interleaving could occur, and so sometimes you might see the bug, and sometimes you don't. Okay, and in fact, during the testing stage of creating your program, you might never see the bug. Okay, because the bug can be quite rare. But once you deploy this to users, right, then they're going to keep using your program, and probably if there's a bug out there, then eventually one day they're gonna hit on it, right, and the program will crash. Or even do something worse. Okay, and also it's hard for people to anticipate what kind of bugs could be in the program. Okay, because these bugs occur as the result of interactions between many different threads, right? And people have a hard time keeping track of all the ways that a bunch of different things can possibly interact. Right? There's an exponential number of ways that they can interact, and just people aren't. They aren't used to thinking about that, and sometimes they're not even capable of thinking about that. Okay, so today we're going to look at some ways to deal with concurrency bugs. Right. So before that, I just want to mention that so this is not just a hypothetical problem that these bugs can occur. Right. So they've actually occurred in practice and have had serious consequences. So, for example, there was a machine which output radiation to treat cancer patients called Theric-25. And this one had a concurrency bug, and this led to the device outputting too much radiation, and this actually killed several patients. Okay, there was another bug where for the first launch of the American space shuttle, there was a concurrency bug in the avionics software. And so this was discovered like right before the actual first launch, right? And so they had to abort the first launch. Okay, so these problems definitely occur in practice. And in fact, nowadays, they are going to occur more and more in practice because we have more and more programs which are parallel or which are concurrent. Okay, so previously, right, we mostly had single processors, right? At least most users, they would only be encountering single processors, single-threaded programs, right? But nowadays, basically everything is multi-threaded or multi-processor, and so we need to have programs that take advantage of this for performance reasons, but those programs are much more likely to encounter these concurrency bugs. Okay, so we have to have some way to deal with this. Okay, so there are a number of different ways of dealing with this. So I'll go through a few of the main ones. So the first one so this is something we talked about last time, is these things called critical sections or locks. Okay, so remember the critical section is basically, so both critical sections and locks only let one thread sort of do something at a time. Okay, so the difference between the critical section and lock is that for the critical section, you're saying there's some block of code, your critical section, which only one thread can access at a time. Okay. Whereas for the lock, that's more about protecting a single piece of data, so that there's only one thread modifying the data at a time. But basically, the idea is that there's some sort of resource, right? Either the code or the data, that you only allow one modification, one thread to modify at a time. And so in fact, a more general term for this would be mutual exclusion, okay? Because if you have multiple threads, then they mutually exclude each other. You can only have one thread doing this action at a time. Okay, so these critical sections and locks, they can be very effective for resolving concurrency bugs. Okay, because if you suspect that there's some sort of sequence of actions in your program that you suspect something bad would happen if multiple threads ran concurrently, then you can just put a critical section around that block of code, and so that would eliminate the problem in most cases. Okay, and it's also easy to use because you can just using a few keywords, you can define your critical section. However, you don't want to overuse these things because they can also cause a number of problems. Okay, so for example, they cause contention between the threads, right? Because if you have a block of code and you put a critical section on it, then when multiple threads run your program, right, they need to contend to have access to that critical section. Okay, and the threads that do not get into the critical section, they would have to wait, right? So that serializes your code. It causes it to go from a parallel code to sequential code. Okay, so you can lose performance. And sometimes you can lose a huge amount of performance by adding too many critical sections. Okay, so when you use these things, you need to decide how much stuff to put into a critical section or a lock. Okay, because as I said, if you put too much, you're going to lose your parallelism and your code won't perform. Okay, but if you put too little, right, then maybe it's not enough, and so you haven't actually sufficiently protected your code, and you haven't eliminated the concurrency bug. Okay, so it's kind of hard to judge how much you need to use them. Okay, some other issues with these are that if you have several processes, right, and so we saw last time that we had an example with two processes trying to get two resources, locks on two resources, right, and if they don't do it the right way, then they can actually deadlock, meaning that they're both just stuck forever. Okay, so when you try to get multiple locks, you need to have some way of regimenting these processes so that they don't deadlock. Another problem is called priority inversion. So this is where a low priority thread acquires a lock before a high priority thread. Okay, so in that case, the low priority thread will get to run, but the high priority thread needs to wait. Okay, and that's not what we want because we actually want the high priority thread to run. Okay, but because of locks, you can actually get this priority inversion. Now, the thing is that people have recognized these problems for a long time, and they have various ways of dealing with them, some more effective than others. But locks today are still the most popular way of doing concurrency programming, concurrent programming, okay, and eliminating these concurrency bugs. And so that's why today we're going to be looking closer at locks, and in particular, we're going to look at how to efficiently implement locks, okay? Because right now we've been talking about locks at an abstract level. We just said that somehow the system provides for us this capability of ensuring mutual exclusion. Okay, we haven't talked about, well, how does the system do that, right? And can it do it efficiently? Okay, so we're going to talk about that later. But first, let's look at another way that we have of eliminating these bugs, which is called transactional memory. Okay, so here what's going to happen is that we have a block of code, and we're going to define this as a transaction. And that basically means that this code is either going to execute atomically, right? So we're going to execute all of the steps of this code, and we're not going to get interference during this execution from any other threads, right? So either we do this atomically, or we don't do it at all. Okay, it's all or nothing. Okay, if we do it, right, then we're guaranteed that no other threads are interfering with us as we execute. Okay, so the way that transactional memory works is that the transactional memory system is going to keep track of all of the reads and writes which are done by the transaction. Okay, so the only way that threads can interfere are that so the threads are doing read and write operations. Okay, so if they're only doing reads, right, then the state of the system is not being modified, and so we don't have any interference between the threads. Right? The only way we can get interference is if some of the threads modify the state, right? And then maybe the other threads are not aware of that modification, and that would cause problems. Okay, so therefore we want to keep track of which reads and writes are happening in the transaction, and now if so the threads are reading and writing to different memory locations. But if there is a memory location where several concurrent threads both read and write to that location, okay, then we could potentially have a bug. And in that case, the transactional memory system is going to abort all of the transactions except for one. It's only going to let one of those transactions that access this common memory location proceed. Okay, all the other ones get aborted. Okay, and also when you abort a thread, you're going to undo all the changes it made. Okay, so because a transaction can consist of multiple actions, so you could have two threads that have done a number of different actions, and then they both try to access a common memory location. Okay, and then you have to abort one of the threads, but then you also have to undo all of the previous actions it did. Okay, now if you have two concurrent transactions and they access completely different memory locations, right, then there's no way for them to cause problems for each other, right? You won't have any concurrency bugs. Okay, so in that case, you can actually let both transactions commit. Okay, they both can do all their actions. Okay, so therefore, the nice thing about this transactional memory is that it prevents bugs when you need it to, but it lets you have parallelism when it's possible. Okay, so what I mean by that is if there is a conflict, right? If you have two concurrent transactions and they read and write to the same memory location, right? Then potentially there's a bug, and then our transactional memory system detects that bug and prevents this happening, right? By aborting the other transactions. Okay. On the other hand, if we're in a situation where there can be no bug happening, right? Because the transactions are accessing different memory locations, then all the transactions can commit. And in that case, we have parallelism, okay, and good performance. Okay, so that's why people think that transactional memory is a promising piece of technology. And in terms of where it is currently, right? Do we have transactional memory in our in the systems that we use? Well, so there are actually two types of transactional memory. So there's a hardware transactional memory and software transactional memory. Okay, so hardware transactional memory is actually being handled in the processor. Okay, and there are commercial processors that implement some sort of hardware transactional memory, like you have processors from Intel and Sun and IBM that have capabilities for transactional memory. Okay, however, there are also limits to what they can do because they're working in hardware. Okay, so for example, remember that the transactional memory needs to keep track of which reads and writes are being done, right? And so therefore, you have to have, if you're doing this in hardware, you have to have some hardware that's actually keeping track of this stuff. Okay, and there's a limit to how much hardware you can devote to keeping track of these reads and writes. Okay, so therefore, hardware transactional memory has a limit on the size of the transaction that it can handle. Okay, so maybe it can handle transactions with a few hundred expressions, but not more than that. Okay. And then also there's limits on the types of transactions it can handle. Okay. However, because it's being done in hardware, then it's usually quite fast. Okay, so you get good performance, but you can't handle all types of transactions. So on the other hand, you can do this in software, and there it becomes a lot more flexible because, for example, to keep track of the reads and writes, right, you can just sort of store that in the memory of the processor, okay, for the processor. Okay, so then you can deal with much larger transactions. However, because you're doing this in software, then of course it's going to be a lot slower. Okay, so you'll get so currently the software transactional memory systems usually obtain pretty poor performance. Usually it's almost it's unacceptable. So people are currently not using these too much. Okay, so there's critical sections, there's transactional memory, and then lastly, if you want to have correct code, then you can just try to write correct code. Okay, try to write correct concurrent code. But this is really hard. Okay, it's hard for everyone basically. Okay, especially for programmers who are on a deadline. They can't write really large pieces of concurrent code and be sure that there are no bugs. Okay. In fact, even pretty simple concurrent programs that are both correct and efficient, okay, even these would qualify as sort of research as research level material, and you can get these types of algorithms published. Okay, so therefore, transactional memory is not ready for prime time, and just sort of forcing people to write their own concurrent code is not really a practical solution. So therefore, we're still going to go back to the old solution of critical sections and locks. Okay, so we're going to focus on this problem. So both critical sections and locks achieve this property called mutual exclusion. Okay, so then we're going to talk about mutual exclusion. So mutual exclusion, there are basically a few properties that a mutual exclusion algorithm needs to satisfy. So let's talk about these. So the first, all right, so what we're trying to do is we have, let's say, n concurrent processes. Okay, so that means that they're running at the same time, and they could be running at different speeds from each other. Okay, and they want to obtain some sort of resource, which we're going to call a critical section. Okay, so it's just some abstract resource. It could be a piece of code, it could be a memory location, but it's just some abstract thing. Okay, so then what we need the the mutual exclusion algorithm to achieve is, first of all, we want the mutual exclusion property. Okay, so that's the first property here, which is that we do not have two processes in the critical section at the same time. Okay, so that's the basic property here. And then second, so this first property is a safety property, right? Because if we don't satisfy it, then our code can potentially do something bad. So that's like a violation of safety. Okay, but we also want to make sure that our system makes progress. Okay, for example, one way that we can satisfy the mutual exclusion property is that we just stop all the threads. Okay, nobody can do anything. Then of course we're all safe, right? But that's useless because we're not actually doing anything productive. So therefore, we need a progress property. And so there are different progress properties that you can define. So one progress property is called deadlock freedom. Okay, so this just says that your system does not deadlock, right? Meaning that you don't have a situation where everybody is stuck. Okay, so another way to say this is that if we have several processes that want to enter the critical section, then at least one of them will succeed eventually in some amount of time. Okay, I mean these guys need to do some sort of coordination, so they're going to run some algorithm. So it takes some time for one of them to get into the critical section. Okay, but eventually, after some amount of time, if you have multiple processes that want to enter the critical section, then one of them gets to enter. Okay, and likewise, if you just have one process that wants to enter the critical section, then of course that process will also get to enter. Okay, but at least we're not going to have everybody being stuck. Okay, so now you can ask for even more than that. Okay, so you can require a stronger progress property, which is wait freedom. So this one says that if several processes want to enter the critical section, then every process gets to enter in some finite amount of time. Okay, so the deadlock freedom is just there might be one process that can enter. Okay, and that process maybe can enter multiple times, in fact, because it can enter the critical section and then come back again and then enter again. Okay, so that would be fine. That's fine for deadlock freedom. Okay, but in wait freedom, you want to make sure that eventually everybody gets a chance to enter the critical section. Okay, so like maybe let's illustrate this with an example. So suppose you have let's say 3 processes. Okay, 1, 2, 3. Right now. So here are the processes. Now, if you just satisfy deadlock freedom, so let's say all 3 processes want to enter the critical section. Okay, so if you want to satisfy deadlock freedom, then maybe the first time process 1 enters the critical section. Okay, but then afterwards, so then he's going to do his stuff and then exit the critical section. But then maybe afterwards, process 1 wants to enter the critical section again. Okay, right? So maybe it's like this process is like taking some items out of a queue. Okay, so it got into the critical section, took the item out, but then now the thread keeps running and maybe it wants to take out a second item. Okay, so then in that case, 1 is going to come back, and again, 1 is going to compete with processes 2 and 3 to enter the critical section. And so if we just have deadlock freedom, then maybe 1 could win again. Okay, and then after the second time, 1's again going to come back. Okay, but then this time maybe 2 wins. 2 gets to go into the critical section. Okay, and then 2 is going to come back for a second time, and then now we have 1, 2, and 3 competing, and let's say 1 wins again. Okay, and the next time 2 wins again, and then so on. Okay, but the problem is that 3, right, process 3, he wants to enter the critical section, but he never wins, right, because you have processes 1 and 2 who keep entering, right? So now our system overall is making progress, right? We're not deadlocked because threads 1 and 2 are entering the critical section. Okay. However, we don't have wait freedom because process 3 never gets to enter. Okay. For wait freedom, we require that every process eventually gets to enter. Okay, so if we want wait freedom, then maybe here, right, instead of process 2 succeeding, we need process 3 to actually at least succeed once. Okay, we're not asking for strict fairness, right? We're not asking that 1, 2, and 3 succeed the same number of times, right? But at least if 3 has been waiting for a long, long time, he's got to at least eventually get one chance to go into the critical section. Okay, so that's wait freedom. Okay, now it's usually much easier so any mutual exclusion algorithm has to satisfy the first property, the mutex property, right? This one over here, right? Because if you don't satisfy that, then the algorithm is useless. It's not doing anything. Okay, and the algorithm has to satisfy some sort of progress property, right? Because otherwise, nobody can make any progress. Okay, but usually it's much easier to satisfy the deadlock freedom property than the wait freedom property. Okay, meaning that you can write very efficient algorithms that satisfy deadlock freedom, but if you require the algorithm to be wait free, then the algorithm must be much more expensive. Okay, and oftentimes it's not really worth the cost to write such an expensive algorithm. Okay, so therefore usually we just we're satisfied with just having an algorithm that's deadlock free. Okay, and also even if you have a deadlock-free algorithm, oftentimes in practice it works as a wait-free algorithm. Okay, meaning that even if your algorithm is is only guaranteed to be deadlock-free, if you have the situation with like 3 threads, right? It's very unlikely that in your executions that you'd only have 2 threads always winning over and over. Okay, because the actual execution depends on a bunch of sort of random factors, right? Like how the threads are interleaved and so on, right? So even though there could be interleavings where 3 is always locked out forever and never gets in, right? Those are unlikely to happen, especially if you run for a long time. Okay, so therefore, if you just take a simple, efficient deadlock-free algorithm, pretty much you're guaranteed that eventually everybody gets into the critical section. Okay, so so what we're going to do is try to implement these mutual exclusion algorithms. Okay, so we're going to look at how to implement these, and the type of algorithm that we have depends on the what kind of operations your hardware supports. Okay, so for example, all processors support read and write operations, right? But they could support additional synchronization operations in hardware. Okay, so for example, we have things called test and set or compare and swap. Okay, so many processors support these options, not necessarily all processors. Okay, and there are other functions like load link store conditional. Okay, there are some processors that support this, and many others that do not support it. Okay, and maybe even like multi-word compare and swap. Okay, we could there might be hardware that supports this operation, but definitely not all hardware supports it. Okay, so if you have these additional operations, right, it makes it easier and more efficient to write mutual exclusion algorithms. Okay, so therefore we're going to look at different types of algorithms based on what operations they actually use. Okay, so before that, let me first talk about these 2 synchronization primitives, test and set and compare and swap. Okay, so so for test and set, so what we have here is we apply test and set on a Boolean variable x. Okay, so so this test and set basically tells us if x is true or not. Okay, so suppose that x is initially false. Okay, then if you do test and set, right, you get back a response which is false because currently x is false, and furthermore x gets set to true. Okay, so this test and set does two things. It tells you x's current value, and it sets x to true. Okay, and it does both steps atomically. Okay, so there are two steps happening. You can do this with a read and write operation, right? You can try to do this with a read and write, right? So you can just read x, right, and then you can set x to true. Okay, but if you do it that way, then those two steps are not guaranteed to be atomic. Okay, the test and set, it'll do both steps atomically without interruption from other threads. Okay, and it turns out that this is very useful. Okay, so again, if x is currently false, right, then our response is false and x gets set to true. And if x is currently true, right, then the response we get from test and set is true and x doesn't change, x stays true. Okay, all right, so there's something similar to test and set, which is get and set. Okay, so oh sorry, so there should be like a value here. Okay, so yeah, so there are two arguments. So there's the variable and then there's a value. Okay, so get and set is generalizes test and set because for test and set x is a Boolean variable, right? It's either true or false. Whereas for get and set, x can have any value. Let's say it's an integer, okay? And what get and set does is that it gets the current value of x and then sets it to a new value v, okay? So for example, if x is currently 0, right, and then v is 5, then if you do get and set of x and 5, then we get back the response 0, right, the current value, and then x also becomes 5. And both these happen atomically. Okay, so next we have this compare and swap operation. Okay, so here we have a variable x and then two values, v and v prime. Okay, so the compare and swap is going to test if x is currently equal to v. Okay, if it's currently equal to v, then x gets set to a new value, v prime. Okay, but if x is not currently equal to v, then x doesn't change. Okay, so and also it returns x's current value. Okay, so for example, suppose x equals, let's say 5 right now, right? And if you do compare and swap of x and then 5 and then 10, right? Then we get back the response 10, right? So then we, how do we say this? So then we get back, let me write that, get back 5 because the current value of x is 5, and then x now is equal to 10. Okay. However, if you do compare and swap of x and then 6 and then 10, right, then nothing's going to happen because we're going to compare the current value of x, which is 5, to 6, right? They're not equal, so therefore we do not set x to 10. Okay, so we still get back get back 5, and then x continues to equal 5. Okay, and again, all these steps are happening atomically. Both the comparison of x to the value v, right, and then potentially setting it to v prime. Those steps happen atomically. Okay, yeah, and it turns out that if you have, especially the compare and swap operation, if you have compare and swap, you can actually implement sort of any algorithm, any concurrent algorithm. Okay, for test and set, it's actually not sufficient to implement certain algorithms. Okay, but once you have compare and swap, you can implement any algorithm. And but we're only interested in the mutual exclusion algorithms, and it turns out that using either compare and swap or test and set, we can implement mutual exclusion. Okay. Now, something else that we need to be aware of, we won't worry too much about this, but there's also this issue of processor's memory model. Okay, so memory model means a processor can have either strong or weak memory models, right? And the processor can also do things like reorder instructions. Okay, so previously we I think in one of the very early lectures, we saw an example where if a processor can reorder certain instructions, then it can get more parallelism and higher performance. Okay, so real processors do reorder instructions, but if your processor does that, it can actually break many lock algorithms, right? Meaning the lock algorithm works correctly if you don't reorder anything, but once you allow reordering, right, then the algorithm can fail. Okay, so most lock algorithms assume a sequentially consistent memory model. So that just means that if you have like a process that it's supposed to do a sequence of steps, right? Let's 1, 2, 3. Okay, then those steps do not get reordered during the actual execution. They can get interleaved any way you want with other processes, but they're not going to get reordered. Okay, so now we know what mutual exclusion is. Now let's try to implement mutual exclusion. Okay, so we're going to start with a simple example. And in fact, this example, this algorithm does not even work correctly. Okay, but it illustrates the basic concept, and then we can modify this a bit to have a correct algorithm. Okay, so what we're going to do is we just to start out with, we just want to implement two-process mutual exclusion algorithm, mutual exclusion. Okay, and we want to just use basic read and write operations. Okay, so then the way this works is if you have two processes that want to get into a critical section, right, then they basically have to be aware of each other so that they don't go into the critical section at the same time, right? So you need some way for the two processes to notify each other. Okay, and the way this is going to happen is that we're going to have these shared variables, these flags that the processes have. So two processes, and each one is going to have a flag. If the flag is true, right, then this tells the other process that I want to enter. Okay, so I've got a flag. If I raise my flag, it tells the other guy I want to enter the critical section. Okay, and the other guy has a flag also. If he raises his flag, then I know that he wants to enter also. Okay, so the algorithm is very simple. All you do is if you want to get into the critical section, right, so then to do that, you call the lock function. Right, I want the lock, meaning I want to get into the critical section. Okay, and when I do this, I just raise my flag. Okay, I tell the other guy I'm trying to get in. Okay, and now to prevent both of us from getting in, right? So to satisfy mutual exclusion, I'm just going to say that okay, if I see the other guy's flag is up, right, I'm going to wait for him. Okay, as long as his flag is up, I'm going to keep waiting. So I have this while loop over here, right? So if he raises his flag for a long time, then I'm going to wait for a long time. Okay. All right. So that's the lock algorithm, and then the unlock algorithm is just that. This means that I'm done using the critical section. Okay. And then now I'm just going to lower my flag. Okay, because I don't need this anymore. Okay. Yeah. So so that's the algorithm. All right, and it turns out that this is partially correct, this algorithm. Okay, so this does satisfy mutual exclusion. Okay, so for example, yeah, so to show this, suppose you have two threads A and B. Okay, so then one of them is gonna, so if they want to get into the critical section, right, they're gonna call the lock algorithm, and so they're both going to do line 7. Okay, and then one of them is gonna do line 7 first. Right, because they have an interleaved execution, but one of them is going to do line 7 first, right? And so let's just suppose A does line 7 first. Okay, so A does line 7, right? So here you have processes A and B, right? So A does line 7, and then maybe later on B does line 7. Okay, and then we don't really know what A does, but we know that eventually B is going to do line number 8. Okay. But when B does line number 8, right, he's going to see that, oh, okay, when A did line 7, right, A set its flag to be true. So B is going to see that, right, because B is going to read, oh, I forgot to say this, but basically here you have two variables. So I is like myself, okay, so if I'm thread 1, then I is 1. If I'm thread 2, then I is 2. And then J is the other guy. Okay, so here I'm setting my own flag to be true, and I'm checking the other guy's flag. Okay, so now in our example, right, B would check A's flag and see that it's true, right, because A's already done line 7. And so therefore B is going to wait. Okay, So therefore, definitely if A wants to get into the critical section, B is not going to also go into the critical section, right? If A did line 7 first. Okay, so always we're going to have one of these processes is going to do line 7 first, and so the other guy will be waiting. And so therefore we don't have both processes in the critical section, and so therefore we satisfy mutual exclusion. Okay, however, this algorithm is not going to make progress in certain cases. Okay, it's not deadlock free. Okay, it's definitely not wait free, but it's not even deadlock free. Okay, and the reason is basically if you have two processes that both want to get into the critical section, right, then they can end up waiting for each other. Okay, so for example, suppose you let's go back to this execution. Okay, so then A does line 7, B does line 7, right, and then we have let's say B does line 8, and then A does line 8. Okay, so this is like time, going down over here, right? Yeah. All right. But then B is going to see that A wants to go in to the critical section, and B is going to be waiting at line 8. Okay, so he's going to spin at his line 8, right? And then likewise, A is going to see that, oh, okay, B has already indicated he wants to go into the critical section, right? So A is going to spin at his line 8. Okay, and now both of them are just going to spin forever because neither of them, well, you see that they're stuck at this line 8 over here, right? So they can never, so they can never get into the critical section. Okay. So this is basically like the situation where you have two people who are too polite with each other. Okay, so let's say that you and I are both trying to go through a door. Okay, so then if I'm polite to you, if I see that you're trying to go through, I'll let you go first. I'll wait for you. Okay, but if you're also very polite, you're going to wait for me. Okay, so then if we're too polite, we're just going to end up waiting forever for each other. Okay, and that's what's happening with this algorithm. Okay, so now we need to we're going to see how to modify this algorithm a little bit so that we get progress. Okay, so of course we still have mutual exclusion property, but we also now have progress. So this new algorithm is called Peterson's algorithm. So again, this is only for two processes. Okay, and it's basically the same as the previous algorithm, but so we still have these flags. Okay, so if I want to get into the critical section, I'm still going to raise my flag. Okay, but now we have this additional thing called victim. Okay, so victim is going to be one of the processes. Right, and what happens is that if I want to get into the critical section, I'm going to call lock. Right, so then I raise my flag in line 8 over here. Right, and then I set victim to be myself. Okay, and what this is trying to do is saying that I'm going to wait for you. Okay, victim is like the guy who does not get into the critical section, right? So and then a victim equals I means that I am sort of going to volunteer not to go into the critical section. Okay, but if you want to go into the critical section, you also volunteer not to go into the critical section. Okay. So it seems like the previous problem that could occur, right, this deadlock problem, could occur again with Peterson's. Okay, but the reason it doesn't occur is because this victim here, right, is shared by both of us. Okay, so we write to the same victim variable, right? That's different from the flag where each of us has a different flag, right? I've got my flag, you've got your flag. Okay, so we have two flags. Okay, but there's only one victim variable. Okay, it's being shared by both of us. Okay, so yeah, so it's kind of like, imagine we have a common whiteboard that, or a blackboard that we can write to. Okay, so if I want to go through this door, right, if I want the resource, I'm going to write my name on here. Okay, meaning that I'm going to be waiting for you. Okay, but then if you also want to go in, right, then you're going to erase my name, right, and then write your name. Okay, so now you're gonna wait. Okay, so that's what line 9 here is doing. Okay, and then line 10. Okay, so then how do we decide who goes in? Right, we're gonna again look for the other guy's flag. Okay, now if the other guy's flag is raised, so he wants to go into the critical section. Okay, and victim equals I, meaning I'm gonna wait. Okay, victim equals I means I'm going to wait for the other guy. Okay, then I will actually wait. Okay, so if I see you want to go in and the victim is myself, then I'll wait. Okay, but if I see either your flag is false, okay, so you're not trying to get into the critical section, okay, right? Then I'm not going to wait for you, okay. Or if I see your flag is up, but you volunteer to be the victim, okay. So if victim is not equal to I, it's equal to the other guy J, right? Then I'm also not going to wait, okay, because you volunteer to be the victim, so I'm going to go through. Okay, so that's the algorithm, and now let's check that it still works correctly, or actually it works more correctly because now we have all the properties, right? So first of all, we check that it satisfies mutual exclusion. So so now let's look at line 9 over here, right? Now, whichever, let's say that process I is the process that did line 9 last. Okay, so both processes are going to do line 9. One of them is going to do it last. Okay, so therefore they've already done line 8, right? So they've both set their flags to be true. Okay, so therefore, since I does 9 last, right? Then the final value of victim is going to be equal to I. Okay, plus since the other guy J has set his flag, right? Then when I gets to line 10, he's going to have both conditions satisfied. So he's going to wait for 10 for the other process. Okay, so definitely I is not also going to go into the critical section. Okay, so we cannot have both processes in the critical section. So therefore we have mutual exclusion. Now next we need to make sure that we now have a deadlock-free algorithm. Okay, and here the reason is that the only way you can have deadlock is is if both processes are waiting, right? And the only place where you wait is this line 10 over here. Okay, so we just need to check that you cannot have both processes waiting at line 10, right? Now you see that none of the other lines involve any sort of while loop, right? So there you do an instruction and then you're done with it. Okay, the only way you can be stuck is if you're somehow stuck at line 10 over here, okay, in the while loop. But the reason you cannot have both threads be stuck is because if you look at the thread that did line 9 last, okay, that guy set, okay, so that guy set victim to be himself, okay, so only that guy can have both conditions be true, right, can have victim be equal to himself and see the other guy's flag, okay. The other guy who did line 9 first, right, then you know, he might see the other guy's flag up, but victim will not equal himself because he did line 9 first, and then the other guy did line 9. So then the other guy switched victim to the other guy. Okay. Yeah. So so that's why this algorithm is deadlock free, and this algorithm is also wait free actually. Okay. So even though this only works for 2 processes, you can actually sort of connect many copies of this. You can put many copies of this algorithm together in order to get an M process mutual exclusion algorithm. Okay. All right. So oops. Okay. So next, we're going to look at something called Lamport's algorithm. Okay, so Lamport's famous bakery algorithm. So this is another mutual exclusion algorithm, and this is designed for M processes, not just 2 processes. Okay, so all right. So the reason it's called the bakery algorithm is because it involves this ticketing process, which is kind of like how you go to a bakery and to figure out who gets the bread first, right? Everybody takes a ticket. Okay, and then you get served in the order that you take your tickets. Okay, so in fact, this code has, you can look at the code as having two parts. Okay, so the first part is called the doorway part, and this is where you get a ticket. Okay, at a bakery, and then the other part is a waiting part. Okay, so that's after you get the ticket. Now you're gonna wait for them to call your ticket, and we can show that. The doorway part, right? Everybody finishes the doorway code in a bounded number of steps. Okay. basically because there's no while loop in the doorway. Okay, the only while loop is in the waiting part. And this bakery algorithm has this nice first come first serve property. So what it's saying is that if one process I finishes its doorway section, okay, so the doorway section is a few lines of code. So if it finishes all those lines of code before another process J even starts the algorithm, okay, then I will definitely enter the critical section before J. Okay, so that's this first come first serve property. Now, if it happens that both I and J are running their doorway sections of the code concurrently, right, then we don't know who's gonna go into the critical section first. Okay, but if I comes really well before J comes, right, like if I'm completely inside of the bakery and I got my ticket, okay, and then somebody else comes, okay, then that guy's not gonna get his stuff ahead of me. Okay, so because of this first come first serve property, then you can show this algorithm is actually a wait-free end process algorithm. Okay, because we said that every process eventually finishes its doorway section, right? Because there's no while loops in there. Okay, and then after that, after I finish my doorway, then the only threads which can go ahead of me in the critical section are the ones that are also in the doorway right now. Okay, if somebody is not in the doorway right now, right, then he is going to be one of these J guys who starts his algorithm after I finish my doorway. Okay, and then by the first come first serve property, he's going to enter after me. Okay, so the only guys that can enter before me are the guys concurrent with me, right? And there's only a finite number of those, and so therefore I'm never going to have to wait forever. I just have to wait for the my concurrent threads to finish. Okay, so let's look at this Lamport algorithm. So here we again have these flags, right? So so now since you have n threads, right, we have n flags. Okay, one flag per process. So again, the flag is just to tell the other processes that I want to go into the critical section. Okay. Now you additionally you have this thing called a label. Okay, so label is just a number. Okay. Right, and then initially all our flags are false and the labels are 0. Okay, so now basically what's going to happen is I'm going to do two things to get into the critical section. I'm going to raise my flag so people know I'm here, right? And then I'm going to get a label, and the label kind of corresponds to my ticket. Okay, and the smaller my label, right, the earlier my ticket is, the faster I get in. Okay, so the place where so here on 13 I set my flag. Right, and then label, I need my label. So if I see a bunch of other threads are already waiting in the doorway, right? So they've all got their tickets, okay? So it's no fair if I take a smaller ticket, right? So I should take a larger ticket, right? So what I'm gonna do is I'm gonna read everybody else's label, right? I'm gonna take the max of those values and then I'll add 1, okay? So I take a ticket that's larger than everybody else's ticket, okay? All right, so then next in line 15 over here, I'm gonna to decide whether I can get into the critical section, I'm gonna look for two things. Right, I'm gonna check all the other processes. Okay, so there are n other processes. I need to know how large n is. Okay, so a priori, let's say I know that at most there's 100 other processes. Okay, so then I'm gonna check all of those other processes, and if I see any other process, K, okay, such that K is trying to get in, right, so his flag is up, okay, and K has a smaller label than I do, then I'm going to wait, okay? So now let's talk about this label a bit. So this label here, this thing over here, okay, this is a number, all right? And now potentially you could have two threads that get the same label. Okay, so for example, suppose the labels right now are, so process 1 has a label of like, let's say 2, right? Process 2 has a label of, let's say 3, right? And then process 3 has a label of, let's say 1, okay? Right, so if I'm process 4, I'm going to come and read these 3 labels, and then I'm going to pick 4 as my label, okay? So this is like P1, P2, P3, P4, okay? Now, it's possible that another process, P5, comes, okay, at basically the same time as P4. And he also reads these labels, 2, 3, and 1, right? And in that case, he's also going to set his label to be 4, Okay, so now P4 and P5 have a tie in their labels. Okay, so this is kind of a problem. Okay, so to deal with this, it's a problem because here we need to compare these labels. Okay, so the way we deal with this is we're going to not just compare the labels, the numbers, we're going to compare a pair. Okay, consisting of both the label and the process ID. So for example, here, right, label, if k is 4, then the label here is going to be 4, 4, right? His label is 4 and his process ID is 4. Whereas for process 5, right, his label, let's say, is going to be 4, 5. Okay, right, because his label is 4, right, but his process ID is 5. So, so if you make these pairs, okay, with a label and the process ID, and then you compare these pairs lexicographically, meaning that you first compare the first digit, right? If this label here were like a 3, right, then no matter what, oops, right, this is going to be less than something that starts with a 4. Okay, right? So ooh, sorry. All right. So but if you start with a 4 over here, okay, then if you have a tie, you now compare the second digit. Okay. And so you can never get a tie in both digits because all the threads have different labels. Okay. All right. So then, so then the condition to whether you enter the critical section is you check if there's anybody else who is flag is up and he's got a smaller label. If there is, you wait for that guy. If nobody is like that, then you go into the critical section. Okay, yeah, so sorry, I didn't show all this. But yeah, but this stuff, these words just say what I was describing. Okay, so now we're going to show that this algorithm is correct. So first, we're going to show the deadlock-free property. So so the reason this is deadlock-free is because at any point, right, if you compare all the labels of all the processes, right, so these labels can be totally ordered. Okay, so meaning that you never get a tie between two labels, as we saw. Okay, so therefore there's some minimum label. Okay, at any time, these processes all have some labels, but there's a minimum label among these. Okay, if there's a minimum label, then when that guy with the minimum label, when he does line 15 over here, right, he's not going to see anybody else with a smaller label because he's got the minimum. So therefore, the guy with a minimum label definitely will not wait at line 15. Okay, so then at least that guy can get into the critical section. Okay, this algorithm, next we want to show it has this first come, first serve property. So, right, so in fact, I forgot to define these two. So I said that there are these two blocks of code, right? So there's the doorway part, right? And then there's the waiting part, okay? So this is actually the doorway here, and this is the waiting part, okay? So now, we're claiming that if some thread I finishes its doorway before another thread J starts the lock operation, right, then I will get into the critical section before J. That's the first come, first serve property. Okay, and the reason this is true is because if I has finished its doorway section, right, then I has obtained a label and he's written that label to his array of label to the overall array of labels. Okay, now you get this process J that starts up, right? So after this, J starts up, and so when J does line 14, right, he's going to end up reading I's label. I's already written his label, and so J's going to read I's label, and then he's going to choose a bigger label. Okay, so J's label is always going to be larger than I's label. Okay, so therefore J cannot get into the critical section before I, because when J does line 15 over here, right, he's gonna he's gonna see that I's label is less than it, right? Because I has already raised its flag, and then I's got a smaller label, right? So J cannot supersede I. Okay, so next we need to show this satisfies mutual exclusion, right? So so to do this, suppose for contradiction we violate mutual exclusion so that both I and J are in the critical section. Okay, and so and now let's just suppose without loss of generality that that label that J has a larger label. Okay, one of them has a larger label. Let's say J. Okay, so then when J does line 15 over here, right? so we're assuming that J is in the critical section. Okay, so when J did line 15, right, then J was J looked at whether I satisfies this condition, right, and then so J must have seen that either I's flag is equal to 0, right, either I's flag is equal to 0, right, or I's label is larger than J's. Okay, because if both I's flag equals 1 and I's label is less than J's, right, then J would wait at 15 and he would not go into the critical section. Okay. Now it's impossible for I's label to be larger than J's because we've already assumed that J has a larger label. Okay, and I's label can only increase; it never decreases over time, right? So once J's label gets so. And then the other possibility is that I's flag is equal to 0, right? But I has not. But I wants to get into the critical section, okay? And he hasn't done line 13. Sorry. Oh, okay, right. So then the other possibility is that I's flag is 0, but in that case, I must not have done line 13 yet, okay? Because if I did line 13, his flag would be true. So therefore, I is going to do line 13 afterwards, and then he's also going to do line 14 afterwards. And when I does line 14, he's going to see that he's going to read J's label, right? Because I here in line 14, he reads everybody's labels. Okay, he's going to read J's label, and then he's going to set his label. I is going to set his label to be larger than J. Okay, which again contradicts this assumption that J has a larger label. Okay, so that shows that this algorithm is satisfies mutual exclusion, and because it's first come first serve, it's also going to be weight free. Okay, so if it's weight free, it's definitely deadlock free also. Okay, so so those are the algorithms we're going to look at based only on read and write operations. Okay, so now we're going to look at some algorithms that use other operations, such as test and set or compare and swap. Okay, so yeah, and it turns out that if we allow these operations, right, then we can actually get very simple algorithms. Okay. Okay, so the first basic algorithm is this TAS lock algorithm. Okay, so what's going to happen is that there's a variable called state. Okay, and this is being shared by all the processes. So all processes see this variable. There's only one such variable, state. Okay, they all see this variable, and initially state is equal to false. Okay, so state is just a Boolean variable. Initially, it's false. Okay. And now, very simply, if you want to get into the critical section, right, then you try to set state to be true. And furthermore, you read state's current value, and if it's false, then you get the critical section. If it's true, then you don't get it, and you have to wait. Okay, so that's the entire algorithm over here. Okay, so you do this get and set operation, and you try to set state to be true. Okay, so basically what happens is, so you have state, right? So this is the state variable. Okay, initially it's false. Okay, and then let's say you have some process 1 comes, right? He wants to get the lock, so then he does line 4. Okay, and that's going to set state to be true, and then furthermore, because we're you get and set, so P gets the current value of state, which is false. Okay, and then the value of state becomes true after the statement. Okay, so P1 is going to see that he can go into the critical section. Okay, because here you only wait while state is true. Okay, and P1 saw that state was false, so P1 can finish its lock operation and get the lock. Okay, now later on, you have another process, P2. Okay, so P2, he's going to do his get and set, right? But now state has already become true. So therefore, when P2 does his get and set, he's going to see true. Okay, and also state continues to be true, okay, because you do this get and set here. Okay. But because P2 saw that state is true, then he's going to wait at this line 4 here. Okay, likewise, if you have a P3, right, then he's going to do his get and set, and then he's going to see that state is still true, so he's going to wait. Okay, so so only the first process that comes can actually, so this guy, okay, he can get into the critical section. The other guys are all going to wait. Okay, now eventually P1 is going to finish his critical section, okay, and then he's going to unlock the lock. So then he's going to set this state to be, let's see, is there a way I can do this? I don't suppose. Yeah, so what I want to do is like, okay, so, all right. So anyways, I want to continue with this timeline. So so just let's do it like this. Okay, so let's continue with this timeline. Okay, so like time is going in this direction, right? So this happens first, and then this happens, and then this happens. Okay, so what I want to show is I want to show some more values of state. Okay, so now after P1 finishes, right? P1 is going to set P1's going to do an action, and he's going to do this. He's going to set state to be false. Okay, now P2 and P3, they're still stuck at this 4 over here. Okay, however, as soon as P1 sets state to be false, then the next time they do this operation, right, one of them will now see, so now let's say P3 takes the next step. Okay, so P2 and P3, they're both spinning at 4. And let's say that P3 happened to spin a bit faster and he took the next step. So then he would see that, oh, okay, right, now state is now false. Right, and then now P3 gets to go into the critical section. Okay, but P2 has to, but when he does that, he's going to set state to be true, and now P2 does his get and set, and he's going to see state being true again. Okay, so then P2 would have to keep waiting. Okay, so that's the entire procedure. Okay, so you have a bunch of processes come, they want to get the lock, right? Whoever, so the lock is currently set to false. Okay, whoever does the get and set first, right? One of them is going to be first. Okay, whoever is first, right? He gets a false value back, and he sets the lock to true. So he gets in the critical section. The other threads all get the value true back, so they wait. Eventually, the guy with the lock, he finishes. He sets state to be false, right? And then these waiting guys are still doing the get and set. And then whoever does the get and set first, right? Then he's going to see state being false, and he's going to get in. Okay, and the other guys keep waiting. Okay, so that's the entire algorithm, and you can see that obviously it's going to satisfy mutual exclusion because there's only one thread that can see state equals false, right? Whoever does the get and set first, only he sees state being false. Okay, as soon as this first thread does the get and set, then get and set atomically becomes true. This is where you need this atomicity property. Okay, get and set is previously false, but atomically gets set to true. And then all the later processes that do their get and set, right, they see it being true, so they wait. So therefore, we have mutual exclusion. And we have deadlock freedom because when the lock is open, right, when it's false, right, then one of the threads will be the first to do the get and set, and so he'll get in. Okay, so then so we always have at least one thread getting the lock. Okay, now this is not wait free because you could have one thread coming in over and over, and then he always is the first one to do the get and set, right? Because you basically have this race to do the get and set between all these waiting processes. Okay, so you could always have one process, one of these guys being the first. Okay, so he gets in over and over, and the other guys have to wait forever. Okay, so next, now this TAS lock, it's correct, but it doesn't perform well. Okay, and the reason it doesn't perform well is because these get and set operations. Okay, these are when you implement this in a shared memory system, right? You need some. You definitely want to have cache coherency for efficiency purposes. Okay, but the get and set is always implemented in a way that causes cache coherency traffic every time you call this function. Okay, and now the problem is that if you have a bunch of threads that want to compete for the critical section, right, they're all calling this function. Okay, so they're all competing with each other. So they send a huge amount of cache coherency messages. Okay, and in fact, the more threads you have, right? So here's a plot of the situation. The more threads you have, the more messages, cache coherency messages they send, and the slower this algorithm becomes. Okay. Now, the ideal lock would be that regardless of how many threads there are, right, to get into the critical section, it takes the same amount of time. Okay, so maybe 1 microsecond. Okay, I can get in. It doesn't matter if there's 1 thread or 100 threads. Okay, it's always going to take me 1 microsecond. Okay, for TAS lock, right, the more threads there are, it's eventually going to take a huge amount of time. And this really performs poorly. So then next, we're going to look at a slight modification called TTAS lock. Okay, so TAS is test and set. TTAS is test and set. Okay, and so the way this works is that basically the previous TAS lock algorithm did a spin on this get and set operation, which caused cache coherency traffic over and over. Okay, so this TTAS lock, right, it is not going to spin on the test and set. Right? Rather, it's going to spin on a regular read variable. Right? It's going to repeatedly read a variable. However, if you repeatedly read a variable, then you can cache that variable in your cache. Right? And then as long as the read variable doesn't change value, you don't cause any additional cache coherency traffic. Okay, the TTAS variable, the get and set variable, whether or not the variable changes value, it's always going to cause cache coherency traffic. The read, okay, the get operation only causes traffic when the variable changes value. Okay, so the state value, just like previously, it was representing whether the lock is currently locked or not. Okay, so if it's currently locked, right, then state equals true. So if I just keep spinning on this state, right, then it continues to be true. So there's no cache coherency traffic. Okay. Right, so this algorithm is basically checking, it's reading the state, okay? Is it true or not? If it's true, I wait, okay? Now, eventually, whoever is in the critical section, he's going to unlock, he's going to set state to be false, okay? At that point, the cache coherency hardware is going to inform the waiting processes that state is now false. So when I do the get, I'm going to read false, okay? As soon as I read false, then I go on to line 6 over here, right? And I try to be the first one to set state to be true. I do the atomic get and set. If I am the first one, then I can enter the critical section, right? If I'm not the first one, right? So if I'm not the first one, then I have to go back to waiting over here. But again, when I wait, I only read. Okay, so that doesn't cause too much cache coherency. So if you look at the performance of the TTAS lock, okay, it's going to be better than TAS lock, but it's not ideal still because because there's still cache coherency traffic happening, and the more threads there are, the more traffic there is. Okay, because the threads still need to be able to get the current value of state, right? So we need the cache hardware to do that, right? And plus, once state becomes false, right, then we're all going to compete to try to set state to be true, okay? And that also causes sort of a conflict between, it causes many messages to be sent on the communication substrate, okay? So so the performance still is going to degrade with number of threads. Okay, so next we're going to look at something called a backoff based lock, okay? So this is so this backoff thing is very similar to let's see, is it, yeah, so it's very, very similar to the previous TTAS algorithm, right? So if you look at this part here, it's very similar, right? The only difference is we have this backoff operation over here, okay? So the idea over here is that, if I'm trying to get the lock, right? So I do this get and set operation, right? If I fail, then that means that there must be somebody else who wants to get the lock, right? And furthermore, suppose I fail multiple times, okay? So I try this once, right? I fail. That means somebody else got in, right? And then I keep waiting, okay? And later on, this state becomes false, and I try this line 9 again, okay? Maybe I maybe I fail again, okay? And suppose I fail multiple times. Then what does that mean? That means there are many other threads competing with me, right? So if there are many other threads competing with me, then maybe I should just lay off a bit and not compete so hard, okay? Because I'm not gonna, if I just compete with these guys, only one of us is going to win, and we're just going to cause a lot of problems, a lot of cache coherency traffic in the meantime. Okay, so instead, if I see there's a bunch of other guys waiting, I'm going to go somewhere else. Okay, it's like if there's a restaurant I'm trying to get into, right? There's 100 people waiting. I'm not going to wait, right? I'm going to go somewhere else. Okay, and then maybe later I'm going to come back. Okay, so later when I come back, there's only 2 people left. Okay, then I'll wait. Okay, so that's what this back off means. Okay, it means I'm going to go if I fail multiple times at this line 9 over here. Okay, then each time I fail, I'm going to go away, and I'll keep going away for longer amounts of time. Because the more times I fail, the more this indicates that lots of people are waiting, and so I don't want to compete with these guys. I just want to go somewhere else and then come back later. Okay, so the amount of time that I wait, I'm going to wait for a random amount of time, right? Because if a bunch of guys are competing and if they back off, but they back off for the same amount of time, then they're all going to come back at the same time, right? So I don't want to back off for the same amount of time. I'm going to back off for a random amount of time between this min delay here, right, and this max delay. Okay, so that's what's happening with all of these back off functions over here. Okay, I'm going to choose a random back off between the min and the max values. Okay, and furthermore, I'm going to increase my maximum delay value each time I fail to get the thread, to get the lock. Okay, so that's the basic algorithm. So it works correctly, just like the previous TTAS algorithm. It works correctly, right? Because the only change was that I end up waiting for a while instead of just purely spinning at this 8 over here, right? Which is kind of a waste of time, right? I'm gonna go away and then back off for a little bit. Okay, so this is right. So this back off idea is actually used in many contention resolution algorithms. For example, in Ethernet, right? We need contention resolution because only one process can send on the Ethernet at a time, and so therefore, if I see a lot of contention on the medium, right, then I'm going to go wait a little bit. Okay, and the amount of time that I wait keeps increasing the more times, the more contention there is. Okay, so for Ethernet, we also have this exponential back-off process. But there's a question how long to wait, right? Because if I wait for too short of a period of time, right, then there might be then after I come back, there could still be a bunch of guys competing, right? So then I'm gonna have to wait again. Okay, so I don't want to wait for a very short amount of time. But if I wait for a long amount of time, right? So for example, if I go to a restaurant and I see there's only one person in line, but then I go wait for like 2 hours, right? Then of course I waited for too long, right? Because that guy probably got his seat after 5 minutes, so I should only have waited for 5 minutes. Okay, so and in fact, in these algorithms, you don't know how many other threads are competing with you, right? Because the only thing you know is that oh, okay, I did this get and set, and I didn't get it. Okay, so that means that somebody's competing with me, but I have no idea how many people are competing with me. So I really have no great way of setting this this back off period. Okay, so in fact, looking for the best back off policy, people are still researching how to do this. Okay, there are many different ways of doing this. Okay, so next we're going to look at a different class of algorithms called Q-locks. Okay, so we'll look at several Q-locks. The first one is Anderson's Q-lock. Okay, so basically what the Q-lock, the basic idea is that we're going to form a queue like this. Okay, a queue of processes, right? And then the first guy in the so this is like, let's say P1 and let's say P4 here, and then P3 and then P2. Okay, right? So the processes are somehow. So I'll tell you how they get into a queue, right? So different algorithms have different mechanisms for building this queue, but basically in the end, you can think of these threads as being in a queue, right? So they lined up, and then only the guy in the front of the queue gets into the critical section. Okay, so he can get into the CS. Okay, the other guys, right? They're just spinning. Okay, so these little circle things indicate that they're spinning. Okay. Now, eventually, this P1 is going to finish with his critical section, right? So then when he finishes, right, then he'll let this guy go in. Okay, the next guy waiting. Okay, but P3 and P2 keep waiting. Okay, so there's different ways to implement this concept of this Q lock. So the Anderson's algorithm, the way he implements it is that he implements the queue as an array like this. Okay, so this is basically the queue here, right? So this is like the head of the queue, right? So initially so we have this circular array, okay? And Anderson's algorithm requires that you know how many processes want to use the critical section. So you have to have an upper bound. Okay, so suppose in our example, we have at most 8 processes that want this critical section. Okay, then you use an array of size 8, a circular array. Okay, and then in this array, all the values in the array are Boolean, so they're either true or false. Okay, and at most there's one true value. Actually, let's see. There's always exactly one true value. Okay, and the true value is basically the head of the queue. And the true value indicates that whoever is at that position, okay, can go into the queue. So what's happening is all of the threads are competing to get a location in this array. Okay, and if you get a location and the value in your location is false, right, then you're not at the head of the queue and you have to wait. And but if you get a location and it's true, right, then you're at the head of the queue and you can go in to the critical section. Okay. And then later, so suppose I'm at the head of the queue. Okay, so in this example here, this is the true part of the, this is the only true value in the queue, right? So this thread A here, he is in the critical section, okay? And all these other guys, right, they get a location in this array, and also they're always going to get a consecutive chunk of locations. Okay, so like the queue starts over here, and it's not like you can have this position and then skip some positions and so on. Okay, it's always you're going to have like consecutive positions being occupied. Okay, but these other threads which want to get into the critical section, they are reading their Boolean variable, and as long as that's false, then they keep waiting. Okay. Now, eventually, this guy in the critical section, he is done, right? He finishes, okay? At that point, he wants to, he's going to leave the critical section, and he wants the next guy in the queue to be able to get in, right? Like, for example, if P4 here, right, if he finishes, right, then he's going to go away, and then he's going to let P3 go, okay? So to achieve that, what you set this flag to be false, right? And then this thread, he's going to set his next flag to be true. Okay, and then now thread B sees that, oh, okay, my flag has now become true. I am now at the head of the queue, and I can go into the critical section. Okay, and then eventually, when this guy, so now let's say he's in the CS, right? So this guy's done, right? Now B is in the CS, right? Eventually he finishes. Right, then he's going to set his flag back to be false, and he's going to set the next one to be true. Okay, so whoever's waiting after B can now get in. Okay. Now, the next thing we should talk about is, so I said that all the threads need to get a position in the queue, right? And furthermore, these positions need to be consecutive, right? Like what we're going to occupy indices 2, 3, 4, 5, 6, right? We don't want to occupy indices like 2 and 4 and 6 and so on, okay? So the way you get these, you get a position is that there's something called a tail, okay? So is that illustrated here? Right, okay, so here we have the tail, okay? So there's this variable here, tail, right? And that's pointing at the end of the queue, okay? So now if I want to get into the queue, if I'm thread C, for example, right? So I want to put myself in the queue so I can get into the critical section eventually, right? Then I'm going to do this get an increment on the tail. And get an increment is going to get the current value of tail, which is 4. So I'm going to say that I now get position 4. And atomically, it's going to set tail, it's going to increment tail. Okay, so this get an increment is another atomic operation. It's going to set tail to 5 atomically. So I get 4, and tail becomes 5 atomically. Okay. All right, and then since we have a circular queue over here, if tail gets to be 8, right, then we're going to take this modulo the size, which is 8, and so then tail will actually become 0. Okay, so yeah, so again, there are two parts. When I want to get the lock, I first of all get a position by doing get an increment on tail. So this puts me at the end of the queue, right? And then I just wait on my slot. I keep reading my slot over and over, okay? If my slot ever becomes true, right, then I can go into the critical section. And there's always one slot that is true, okay? And that slot, whichever thread is in that slot, right, then once he's done with his critical section, he's going to set the next slot to be true. Okay, and that's being done over here. Okay, right. So yeah, so this algorithm actually performs very well, okay, because the only expensive part, right, is this while loop over here. This is line 19 over here, right? But here I'm just so I'm doing a spin, okay? But here I'm reading a variable, right? I'm reading my flag over and over, okay? So we said that the reads do not cause much coherency traffic, right? Because I can cache this variable of flag of slot, okay? And then eventually the guy in front of me, right? Eventually he's gonna set my flag to be true, right? At that point, there's sort of one time point where there's some coherency traffic, okay? But it's quite minimized. So this Anderson's algorithm performs well, okay? Now the one downside to this is that here we have to have a bound, an upper bound on how many threads there are. Okay, so next we're going to look at the CLH algorithm. So this is named after three guys, Craig, Haggerston, and Landon. And this is not going to require a bound on the number of processes. Okay, it's again going to be a queue-lock algorithm. Okay, so again, we're going to be building a queue, but we're going to build a queue in a different way. Okay, so so basically, let's see. Where should I draw this? Let's see where I have room. Okay, so I have room over here, right? So I'm going to draw my queue over here, right? This is also going to have a tail variable, right? And the tail variable is going to point at the current tail of the queue. So again, the head of the queue is the guy in the critical section, right? And then and once he's done, he's going to let the next guy go in. Okay, and to build the queue, we also need to know who is at the end of the queue. Okay, so that we can append to the queue. Okay, so this tail. So when you do your lock algorithm, the first thing is you're going to allocate a new node, right? So suppose I want to get it. Want to get the lock. I'm going to make a new node, right? And then I'll set the tail to be myself. Okay, in line 23 over here, I'll set the tail to be myself. Okay. And then also, so I do this get and set value. Okay, so the get and set. So before I do line 23, okay, tail was pointing over here. When I do line 23, my pred is going to be set to the current value of tail. So my pred will actually be set to the current tail. Okay, oops. Let me label these things. Okay, so this is thread A, this is B, and this is C. Okay, so the C.pred is now going to be equal to B, okay? And furthermore, tail is going to get set to node C here, okay? And then, right, okay. And then I'm gonna see whether my predecessor is locked or not, okay? So initially, all the threads are going to lock themselves, okay? So so initially. Let's see. Yeah. So so here we have this. So every thread has. Every node has a field called locked. Okay. And this is currently locked, and this is locked. And when I start my operation, I'm gonna preemptively lock myself. Okay. And then C here is gonna keep spinning, and then he's gonna keep reading this variable, this locked parameter from B. Okay. As long as that's true, I keep spinning on 25. Okay. Now B is doing the same thing, except for B.pred, right, is pointing at A. So B is reading A's locked variable, right? B is looking over here, and C is looking over here. Okay. Now A is in the critical section, and eventually he's going to finish, and he's going to set his lock to false. Okay. So this guy becomes false eventually. Okay. At that point, then B, right? B was trying to B was reading this, and then B is going to see, okay, so now it's false. Now I can get the lock. Okay, so once A is done, then B can get the lock. Okay, And then B eventually is going to do his unlock, and he's going to set his thing to be false here. And then C was reading that, right? C sees it's now unlocked, and he gets it. Okay, so that's the CLH algorithm. Okay, so we have some examples here. Yeah, and the text just says like what I was illustrating. Okay, so so let's actually go back here. Let's say that this is still true. Okay, so there's one last thing I want to talk about, which is the efficiency of this algorithm. So this algorithm is actually very efficient in most architectures. Okay, because all I'm doing over here is the only sort of spin operation. The only operation I do over and over is this read operation, right? Because I'm just reading my predecessor's locked variable. Now, if I have a cache, right, then what's going to happen is I'm going to sort of pull this value into my sorry, let me not draw it that way. Okay, so how do I draw this? Okay, so suppose C's got like a little cache here. Okay, right. So so if C has a cache, he's going to pull this true value into his cache. Okay, and then when he does the spin on 25, right, C just sort of keeps reading this cache thing. Okay, and that's very fast because it's local. Right, and then eventually B, once he finishes, he's going to set this to be false, right? And then then the false value gets broadcast to C's cache. Okay, so that's sort of only one instance where there's message traffic. Okay, so it's efficient. Okay, the problem is, what if you're in an architecture? So there are some architectures where C doesn't have a cache. Okay, if C doesn't have a cache, then the only way for C to read this b dot locked, right? He's got to read b dot locked. Okay, so this then he would actually have to go to B's processor to read that value, right? So B could be on a different processor. So in order to read this, right, that would be every time I read this, I would have to incur remote memory accesses, and in that case, that's going to be slow. Okay, so yeah, so CLH usually works quite well, because most architectures have caches, but if unfortunately we don't have a cache, then it won't work well. So then the final algorithm we're going to look at is the MCS lock. So this is a famous lock by this guy Melachrome and then Scott. So then this algorithm is going to sort of remove this problem that the CLH lock had, right, which was remote spinning. Okay, so instead what's going to happen is it's still going to be a Q lock. Okay, so let's see, where do I have some room? Okay, so I'll draw over here, right? Maybe I'll draw this. Okay, I'll draw this over here, right? And then let's see. Okay, so we're still going to have this locked parameter over here, right? And then so this is going to be A. This is going to be B, right? And then so this is true. So this is going to be false. The first guy is false, and the second guy is true. Okay, right. Okay, right. And then this is pred.next. Right, and then we have a tail, which is pointing over here, right? And then we have a next. Oh, sorry. No. This is wrong. Oh, okay, right. So sorry, the main difference, okay, between MCS and the previous one, CLH, okay, is that CLH, right? You see that so this is the head of the queue, right? Okay, and this is the tail, and then the weighting direction is towards the head, right? Like C is waiting for B. Okay, there's another guy over here, D, right? Then the tail would be on D, right? And then D would be waiting for C. Okay, so you're waiting. You're looking towards the head of the queue. Okay. Now for the MCS lock, right? You don't look for the head of the queue. Rather, you see that these arrows are reversed. Okay, so the arrow goes from the head to the tail. Okay, because here you have a.next. Sorry, let me make this a bit nicer. So here we have the head of the queue over here, and then this is a.next. Okay, so A is saying, okay, the next guy after me in the queue is C. Okay, and let's make another one to be more general. Okay, so here you have is B. Okay, and then here you have B.next. Okay, and the tail is pointing at C, and then his locked is true. Okay, so this is what's happening in the MCS lock. Okay, so the MCS lock is that, and now instead of B spinning on A's locked variable, okay, B is actually spinning on his own locked variable, and C is spinning on his own locked variable. Okay, so if you spin on your own locked variable, and the spin is over here, okay, you see that, so B is, for example, is spinning on his own locked variable. If you spin on your own locked variable, then regardless of whether there's a cache or not, you're not going to cause cache coherency traffic. Okay, so MCS lock works well even in the no cache case. Okay, now so let's talk some more about how this queue is built up. So you have right. So initially, let's go through the process where we add a new node to the queue. Okay, so currently our queue just has A and B. Right, now suppose the node C comes. Okay, so then we have a node C over here. Okay, so first of all, he's going to do this line here, which is going to get the current value of tail, which is B, right, and set it to the new node, which is C. Okay, and the pred is now going to be so C.pred. Okay, C.pred now is equal to B. Okay. And now what's and so pred is not equal to null, right? Because there is somebody in the queue. And so now what C is going to do is it's going to set its locked to be true here. Okay, and it's going to see that, okay, my predecessor, right? Oh, sorry. So the tail now also switches to C, and C.pred equals B. And now this line says that, okay, my C's predecessor is B, and B's next, okay, is going to be C. Okay. And then C here is going to do line 25, and he's going to spin on his own variable. Okay. Now this other case where if pred equals null, okay, so that means that you're at the head of the queue. Okay. So then if you're at the head of the queue, then you don't have any predecessor, so you don't need to do this stuff from 22 to 25. Okay. If you're at the head of the queue, you can also just go into the critical section. Don't wait at line 25. Okay, so that is the in-queue procedure. The D-queue procedure is something like, so now what you want to have happen is, suppose A has finished, right? So A is currently in the critical section, it's finished, okay? So then what A wants to do is, he wants to now free up B, okay? Now why is B not free? Because right now B is not free because he's reading his own locked over here, and it's true. So B is stuck at this point, okay? So therefore what A wants to do is just set this to be false, okay? So how does A know what to set to false, okay? So A knows because A looks at its next field, and it sees that, oh, okay, it's B after me. Okay, if it's B following me, I'm going to set his flag to be false. Okay, now where is that happening? Okay, so that is happening at the unlock. So here, we would have A be the node, right? So he checks if the next is null. Okay, so it's not null, right? Because the next is equal to B, and so he sets B's locked to be false. Okay, and then after that, A just sort of goes away. Okay, so A goes away. I don't want to draw this because I still need this figure. Okay, but A sets his next to be null. All right, so sorry. Okay, so next, now let me illustrate this condition over here, okay? Because this is kind of a more complicated condition. Yeah, I should actually draw this over here. Okay, so let me illustrate this condition over here. So we have A again, right? He has a locked field, right, which is currently false. And then we have a B here, right? And then we have a tail. Okay, so tail, right? And then this is his locked is true. And what else do we have? Okay, so yeah. Okay, now one complicated thing that can happen is that you could get a Q node next equals so here let's say Q node is A, right? So A wants to exit the critical section. Okay, so sorry, let me just need to do this other thing. All right. So A wants to exit the critical section, and suppose his Q node is null. Okay, so that can mean two different things. Okay, one thing is one possibility is that there's just nobody else around. Okay, so imagine that you don't actually have this B. Okay, imagine it's just A. Okay, right, and then he doesn't have a next. There's only one guy in the queue, A himself, so there's nobody next. Okay, so that's one possibility. The other possibility, okay, which is why you have all this code from line 30 to 34. Okay. The other possibility is that there is a node B that is currently in the queue, okay? However, B, remember that B here, he wants to set his, so B's pred equals A, okay? So here he wants to set A's next equal B, right? That's what B wants to do, okay? But suppose B is has only done line 22, but he has not done line 23 yet. Okay, then A doesn't have a next. Okay, so B is eventually gonna set A's next to be equal to B. Okay, but currently A's next is equal to null. Okay, A's next this is A dot next, right? This is currently equal to null. Okay, so therefore A needs to distinguish between these two cases where A is the first case is A is truly alone. Okay, so A's next is null. Okay. Okay, and the other case is that there is somebody else in the queue, B, but B has not done line 23 yet. Okay. Now the reason A has to distinguish between these two cases is, so this is, let's say, the first case, right? And this is the second case. In the first case, A can just go away because nobody else is waiting for him. Okay. In the second case, A actually has to wait for B to notify A about B's presence. Okay, A has to find out about B because B is going to be waiting on this true flag over here. Okay? And the only guy that can reset the true flag to be false, okay, the only guy is B's next node. The only guy who can unset B's flag, okay, is A. So if A does not find out about B, B is going to be stuck forever. Okay, A must find out about B. So now, how does A distinguish between these two scenarios, right? Number 1 and number 2, okay? So he does it through this line, line 31 over here, okay? Because in line 31, okay, if you're in the first case, then the tail is going to be, first case, there's only one node in the queue, so the tail is going to equal A, okay? In the second case, there are other nodes in the queue, so tail does not equal A. Okay, there could even be like a third node over here, and tail actually equals C. Okay, but definitely tail does not equal A. So therefore, A is going to do this line over here. He's going to compare the current value of tail with himself, right? So Q node here is A, right? And if it's equal to A, then we are in case number 1 here, and then the tail can just be set to null, and A can just return. But if when A compares the tail and if this compare and set fails, then this means that the tail is not equal to A. So we are in the second case over here, right? And then A has to wait for B to set its next pointer. Okay, right? So currently its next pointer is pointing at null. A has to wait for B to set the next pointer to B. Okay. In other words, A has to wait for B to eventually do this line 23 here. B is currently at line 22, and B will eventually do line 23, okay? But A needs to wait for B to do line 23 because A, the only thing A knows is that he is not the only node in the queue. He doesn't know who's behind him in the queue, okay? It's only B that knows that A is in front of me. A does not know that B is behind A, but B knows that A is in front of B. Okay, so that's why A here needs to wait for B to set A dot next. Okay, Yeah, so that explains this part over here, right? Okay, so this, all right, now this algorithm is going to work well even without a cache because, again, the spinning. Okay, so now let me clean this up. Okay, so so there's actually two places where you spin. Okay, there's line 34 and there's line 25. Okay, so now you might spin at line 25 for a long time. Okay, line 25 is this spin over here where you're waiting for somebody in front of you in the queue to free you to go into the queue, to go into the critical section. Okay, and this could take a long time because there could be many guys in front of me. Okay, but when I do this long wait over here, this is again reading to my local variables which are cached. Okay. The other place where you could be waiting is that, remember, you have the situation where here A was, suppose A doesn't, A.next was not set yet. Okay, so B still has not executed this line 23 yet. Okay, so then A needs to wait over here. Oh, okay, so this is also a local wait. Wait until predecessor q node.next equals null. Oh, okay, all right. So this is also a local wait. So that's not a problem, okay? Because here I'm also waiting on a.next. Okay. So, anyways, so this algorithm works better. Would work well in all cases. Okay. So so this is all we have to say about the synchronization algorithms. There are actually many other mutual exclusion algorithms. Okay, so this is like a big topic of research, and it's quite interesting. And yeah, so so next time we are going to move on to a new topic, which is GPU programming. Okay, so see you guys all next time.